Okay, so we've got a couple questions from the reading that we can talk about. We were talking about Maxwell-Planck's and the assumptions that he made, and then also the Taylor series expansion and the approximations oscillators. This is all kind of around black body radiation. We're going to find, I gotta talk slower. We're going to find that a lot of the problems we look at in this first chapter, the 7A reading, all relate to this same idea of things don't behave in discrete ways, like things don't behave as point particles with definite position like we thought. Things behave more like distributed objects, like throwing a handful of sand rather than throwing a ball. So with Maxwell-Planck, this idea of oscillators, black body radiation is is actually a quite difficult problem to solve because you have to take an entire block of material. And the way Maxwell-Planck did this was he said, I'm actually not going to take the outside of the block of material. I'm going to look inside the block of material. I'm going to look at what radiation is coming out from it. And in this way, he modeled each of the molecules attached to each other, each of the metal atoms attached to each other. He modeled them not being rigid things, but he modeled them being attached by essentially like springs. And so those bonds could vibrate, right? The molecules could wiggle around each other, but they wiggled around in a predictable way. And that's where we get to this idea of an oscillator. So an oscillator is a generic way to talk about anything that has that predictable back and forth motion. The first place that we really deal with that, if you're in a physics class, is a pendulum swinging. Right? It moves from one point back to the other. If you make a plot of its motion, it just oscillates back and forth from one extreme to the other extreme, back and forth. It turns out bond vibrations in springs kind of do the same thing. If you displace a spring, it kind of bounces back. If it's a perfect spring, it'll bounce forever. Most things aren't perfect springs. They eventually kind of reach back to losing energy. So what we were looking at, what Maxwell-Planck was looking at with black body radiation was, how do I take not just one of these oscillating pairs, but how do I take a billion of these oscillating pairs and come up with some way to describe the the conversion of this heat energy to light energy? I put in heat or electricity, something that gives energy into the system, and then it starts outputting light. It starts putting out radiation. So that's where we can start, and we're going to find that these things, black body radiation, photoelectric effect, heat capacity, they're all going to have the same type of idea put into them. So Maxwell-Planck came up with an equation that described it, and I'm going to write a simplified version of this. He essentially said there's some energy density, it's got a bunch of constants on top, it's got a 1 over lambda to the 5th on bottom, and then it's got a 1 over e to the a minus lambda on bottom. Right? A is a bunch of constants. This is not a 1. This is like 8 pi hc. That's all just a constant. This A term is also just a constant. This is just a single value. That A term is hc over kT, where that K is Boltzmann's constant. So we've got these two different things, but we can make a plot of how this works out. And essentially what Maxwell-Planck did, he comes up with this equation. We still have to have it correspond to the classical results. It still needs to eventually be like other things. And you're able to take this, and you're able to say, well, what's happening with this portion? This is a 1 over lambda to the 5th. So if I do a plot, plotting as we go by lambda, it's going to start out close. If we're here close to 0, 1 over 0 is going to be like infinity, and it's going to crash out as you get to bigger and bigger lambdas. We can do a similar thing looking at this whole massive term. Now this massive term is a bit of a headache because we've got this e 1 over lambda minus 1, and the question becomes, well, how do we simplify that part? There's kind of two different ways we can go about it. since we live in the technology age, one thing we can do is we can just plot it. And we'll see how this goes. Sorry for people who are watching. We can just plot it and see how it looks. Let's see here. Yep, okay. So I have Mathematica here. Let's see. Taylor series expansion. So I'm skipping around a little bit. So here we go. We can plot the 1 over, I called it x because that was easier for me. The 1 over lambda to the 5th, and then the 1 over e minus x. So sorry, 1 over e to the 1 over x minus 1. This first one does like we expect. It shoots off to infinity at one end, crashes out to 0 at the other end. This second function, this 1 divided by e to the 1 over x minus 1, we can think about this one and we can say, okay, if we're at really big wavelengths, I've got e to the essentially 0. So this is going to be 1 minus 1. Number over 0, this is going to fly off to infinity the other direction. So we can look at that, we can make a plot of that, and it does that. It starts out kind of close to 0, and then it flies off. It'll keep flying off towards infinity as we keep going. This is just plotting to 2. Now what we can do is we can say, well, okay, well, what happens when we put these two functions together? And you can kind of see, I didn't do a great job drawing it on the board, but you end up with this section in the middle. Over at small wavelengths, you go towards infinity with one function. Over at big wavelengths, you go towards infinity with the other function. In the middle here, you get like a little distribution where the two things are working together. And so we can do that. We can take the first function, the second function, and then we can take the two functions multiplied by each other. And you get the actual curve from the Maxwell-Planck distribution. So the reason that it's nice to think about these in these, think about it in these separate parts is it allows us to really kind of consider, well, if I'm going towards infinity one direction, one piece of the function is going to dominate. If I'm going towards infinity in the other, or if I'm going towards 0, the other direction, the other piece of the function is going to dominate. So if I want to understand what's happening at really big wavelengths, which is, really big energies, that would be like the classical case. And I can consider what's going to be happening in that situation. What makes it a little bit easier, where do I have this piece? What makes it a little bit easier is if we simplify this bit. So that's where we get to Taylor series expansions. 1 through 5, how much do you like Taylor series expansions? Lots of zeros, a couple ones. Okay, so let's make this function way easier using a Taylor series expansion. Because I didn't like Taylor series expansions when I first learned about Taylor series expansions because I'd never seen how one was used in a functional, kind of way that makes my life better. And here's how it works. So if we just have the Taylor series expansion of e to the x, it's going to be 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6, plus x to the 4th over 24, that's 4 factorial, plus, and it just keeps going. And eventually, if we have an infinite number of terms, we'll just get e to the x back. Now the question is, why would we go to an infinite number of terms when we can just punch e to the x in our calculator? Well, it turns out our calculator is actually doing it this way. So if we look, here's e to the x, and what we do with the Taylor series expansion is we just start taking different chunks. So I can take, what if I just do e to the x and 1? If I make a plot of this, e to the x generally has a shape like this. And if I just have the value 1, I'm just making a flat line. Terrible approximation, right? E to the x does not equal 1 except if you're way down here at really small values, e to the x is approximately 1. So there's this space, there's some x values where just one term would actually be totally reasonable. As we get bigger, if we take two terms, if we do e to the x plus, if we do e to the x, if we replace it with 1 plus x, that's going to be like starting here and then having a straight line. Still not great, right? It's kind of going in the right direction at least now, but it's still not matching the function very well. Until we start to get to 3 terms. We get to 3 terms, and we have e to the x, and we replace it with 1 plus x squared, and now we've got something that kind of looks like this. And in this situation, we're starting to get to something that actually is resembling the curve. If we can tolerate that amount of error, it's fine. Now, as we start to look at specific restrictions, we can get it, we can make arguments about when this is better to use or worse to use. So I can go ahead, there's one, if I do 1 plus x, oh, typing backwards. And look at it. So you got your straight line, if you plot them on top of each other, plot them on top of each other, still not great with the 1 plus x. If you do it with 1 plus x squared over 2, oops, fix that real quick. X squared over 2, and do the same thing here, plus x squared over 2. You notice the curves start to look really similar to each other now. And if we plot them side by side, it's still not great. But you notice there's a much larger portion where it's starting to match up. If we go to a third term, x cubed over 6. Plus x cubed over 6. Get that cubed term in. Ooh, where's my typo? Oops, I put a question mark instead of a divide. Right, now it's starting to look really close. There are places, and you notice it's starting to fit it a lot nicer. Now, the catch with Taylor series expansions, where they become like magical to me, is there are certain cases where Taylor series expansions work really well. One of those cases is not e to the x, but the one that we're seeing repeatedly over and over again in this chapter, which is e to the 1 over x minus 1. If we do a Taylor series expansion of e to the 1 over x minus 1, we get a similar thing. We get 1 plus 1 over x plus 1 over 2x squared plus 1 over 6x cubed plus so on and so forth minus 1. Now the minus 1 bit on there just gets rid of that bit, and that bit cancels out. So we just have 1 over x plus 2x plus. Now here's where this is nice as x gets really, really large. Let's say x is equal to 1,000,000. So this is 1/1,000,000th. This is 1/1,000,000,000th. This is 1/1,000,000,000th. Do I need to include these terms that are like several orders of magnitude smaller? No. So this is where Maxwell-Planck, in order to get to match toward, in order to show that correspondence that it gets back to the classical observation, this 1 over x expansion actually works out really nice as long as we're approaching, I keep messing up where my mouse is, as long as we're approaching towards really small numbers. So we can look at this and we can see just with 2 terms, just with the, well here we can even get rid of the, just with the 1 plus, if I do this with the minus 1 on here, and I get rid of the plus 1 there, e to the x, just as 1 over x, almost the same. Pretty good agreement. Not great out here when you're small values, where quantum mechanics would really be dominating. But over here, just getting out to 3 or 4, which is a pretty small number still, getting out this direction, your answers just almost exactly match. So what we do, or what is done in the textbook, is we simplify this entire thing by using this Taylor series expansion. This equation becomes 1 over lambda to the 5th times, we're going to have 1 over 1 over x. This is just going to be 8 pi hc x over a. Oh, sorry. Go back to calling it lambda for this case, right, since we're doing this in terms of lambda. So if I rearrange this a little bit, right, this whole thing up front is just a single value. And I have this part that's kind of going off towards, as it's just going up. This part going up the other direction. It simplifies down to just 1 over lambda to the 4th, which is the classical result. So as you get to larger values, making it so this Taylor series expansion, that truncation of dropping all of these extra terms is valid, you end up simplifying your entire equation to just be, it follows a 1 over lambda to the 4th, which is what they observed in their earlier experiments. So for the classical results, that's what they found. So the Taylor series expansion, and here's the problem with the Taylor series expansion. The Taylor series expansion is not always useful. We have to apply it in many different situations. We have to find situations where it is useful. So the problem I always had with doing it in a math class is I never really understood when it was useful. When you start looking at it in physics situations, and you start looking at these cases where you have physical boundaries of going towards infinity or not going towards infinity, you start to come into these cases where it's like, oh yeah, if I can take an e to the a over x, if I can take this term and I can just call it 1 over x, it's way easier for me. And that's where Taylor series expansions become really nice, is when you can kind of say this is all small. Right? All of those things become too small to carry, and you just end up replacing your e of 1 over x with 1 over x. Question?
Sorry, can you explain how we got that right there from the Taylor series?
Okay, yeah, let me do it in 2 steps just to simplify things. What happens is we replace this entire bottom portion with just 1 over x. Sorry, 1 over lambda if we're doing it in these terms, right? Doing it for this particular problem. So if you have 1 over, sorry, because we've got that constant a, it ends up being a over lambda, right? Just a constant factor out front. So if we take 1 over a over lambda, that's the same as multiplying by 1 over lambda to the 5th times 8 pi hc, a bunch of constants, times lambda over a. So just moving that bottom fraction, flipping it over, and multiplying.
Yeah. Thank you.
Yeah, you bet. Now, I've already spent more time on this than I meant to. The main thing that comes out of this, I like 2 important things. One, I like Taylor series expansions. We will use them a couple times throughout the quarter. There are cases, like this e to the x case, not very useful unless you're going to negative values and you're having things that you can truncate, or really, really small values where you can approximate it as 1. This e to the 1 over x, a lot more cases where the Taylor series expansion is useful. We're going to see that in other places throughout the quarter where there's situations where I don't use it, and you might be like, hey, why aren't you using it here? And it's one of those cases where it's not very useful. Or I'm going to be like, oh yeah, this is really useful this time. This is one of those cases where it's actually useful, actually simplifies things for us. So black body, that was black body radiation. It was taking the thing that really changed things around for this was essentially saying that energy is, they use the word quantized, right? It's discrete energy. The way that it was originally thought about was essentially like playing musical notes. Like you have a flute and you can't play, you only have certain notes you can play. No matter how hard you blow through the flute, there's certain notes you can play, there are other notes you can't play. You can make it louder or quieter, but you're still playing the same note. The same thing happens when we go to the heat capacity for Einstein, and we see the same type of situation come up if you look at the Einstein equations for heat capacity. You end up getting a 1 over x squared, and if I do it the simplified way, let me do the full Einstein formula. You get something that's like a 1 over x squared, and you can get something that is in e to the 1 over 2x divided by e to the 1 over x minus 1. And you end up getting a similar mathematical form, making sure I'm not forgetting something. No, I'm doing okay. No, I am forgetting something. Square. So you end up getting a similar mathematical form to what Maxwell-Planck got. You get something that's a 1 over to the power out front. You get something that's got a e to the 1 over x minus 1 term inside a parenthesis on the bottom. So you end up getting these similar mathematical systems because they're using the same kind of principles. Maxwell-Planck was saying that the atom vibrations were restricted. Einstein, for the heat capacity, was also saying the vibrations of the atoms were restricted. He was using a vibrating string, or like an oscillator. If you have a vibrating string, there are certain vibrations that work, there are certain vibrations that don't. And the one that I care most about, photoelectric effect, was doing the same thing for photons being quantized energy, for having discrete energy. The atomic emission spectrum is the one that I think is most interesting, at least in a chemistry class. So the way that the atomic emission spectrum, again, same type of thinking. In order to get these discrete levels where you have one allowed value or the other, they essentially said, what if it was like a standing wave, like a guitar string, where it starts at one spot and the only things that work are if it matches back up where it ends. So this point here, this open circle at the beginning, needs to match up with that closed circle at the end. And as long as it kind of continues the same path, you get this system that reinforces itself. This is actually done if we're looking at a particle. It would be like having a wave that matches back up with itself. So as this wave is distributed around a single electron, now not acting like a point in one space, but acting like a distributed object, only makes sense if that distributed object is matching up with itself and being a continuous object. And you don't just end up with one answer for this situation. You can have a second answer by increasing the vibrations. This one I have a lot of trouble drawing around a circle. I'll try. But you end up with the same type of situation. Where it has to, oh yeah, it kind of looks like a bug splat to me, but weird thing like that, right? Pretend I can draw uniformly, right? You end up with a system where it matches up with itself, where when it ends, it matches up. So there's certain oscillations that are allowed. Now this gives rise to a bunch of different problems we have to deal with. The first thing that this does is it means that we have to start treating objects, photons, which people already treat like particles and waves, but more importantly, electrons, we have to start treating them not like point particles, but like distributed objects, which means those things that we talked about last time, those ideas we talked about are going to come back, and they're going to start to be useful. So the fact that we have a distribution function right, the fact that we have some distribution function to describe where things are, that's going to be something that comes back. And since, not really coincidentally, because of the way that the classical mechanic equations work out, we usually call these wave functions. You notice a lot of the analogies that are made are like sound waves, string waves, these oscillating things that are acting like waves. So we start to call those wave functions because of the math that surrounds them. But it's the distributed functions, the same thing we talked about before. We're also going to have that idea of total energy as the easier thing to track. And that's going to give rise to the idea of the Hamiltonian. Right, and so starting to formulate things in terms of total energy instead of forces. We're going to start talking about them in terms of total energy. And the last thing that we talked about last time that's going to come back is having those orthogonal coordinate systems which allowed us to do some separation of variables. Being able to treat, as long as we got two things that are orthogonal to each other, like an x-coordinate, an x-axis and a y-axis, and we're going to try to find situations where I can deal with the x components separate from the y components. And it's going to make it so instead of having one giant problem, we've got kind of like two small problems. So that's also going to be something that becomes really useful. And this all works for these idea of distributed objects rather than single point objects. Now, these ideas from the classical, these classical ideas get put together with this kind of new quantum thing. And there's some postulates that everyone who worked on this early, they kind of came up with the same founding principles to work from. And these are the postulates of quantum mechanics. We're going to go through those right now. Some of them might not make as much sense as others, but we're going to spend a bunch of time talking about these throughout the quarter. And they're going to be kind of the foundation for how we start to solve these problems. Right? And it was, and again, the thing out of that first chapter, the wild thing about, I just erased it, but the wild thing about the mathematics that Planck and Einstein and Rydberg did, because it was Rydberg who did the did the atomic emission spectrum. They were working off of principles. They were working off of these postulates. They were working essentially from classical ideas and had to completely break the mold of what people were doing in physics and chemistry at the time. They said, we're going to try something really different, but it works if we start to treat things as distributed objects and apply these different ideas to it. And in the process of formalizing this, they came up with a couple things that they said were their core principles, their postulates for how this was going to work. And I'm going to write down the simple version to start, and then we'll get to the more complicated way to say it. So the first one is that whatever thing that we're trying to describe, there's going to be a function that defines the system. This is going to be our wave function. Right, so the wave function is going to define everything that we're trying to say about the system. The wave function is just going to say it all. And it's going to be just like one of our distributed functions. There's some mathematical object that does that. The second thing that they said was that acting on the function And this isn't the words they put them in, this is the words I'm putting them in for the simple versions. The complicated versions sound very technical. Acting on the function is an operator. So acting on the function is an operator. Any observable that we want to know. So if we want to know the energy, if we want to know the position, if we want to know the momentum, that's what I mean by observable, something that we would measure about it. Any classical observable has some quantum operator that we can also associate with it. This is also going to lead us to, well, no, that's not it. So there's going to be certain operators that we have that relate to these things. We have to figure out what these operators are. Mostly I'm just going to tell you the operators we're using, but there's some operator that corresponds to whatever measurement we want to make. The ones we usually do are position, momentum, and energy. Those are the three that we usually do. The third postulate is a measured result. Right? A measured result must be one of the possibilities from the operator. Right? This gets to this starts to get towards the discrete idea. You've got this answer or this answer, not an in-between answer. So when we start working on these problems, we're going to find that there are certain values we can get out of the operation. Any measurement we make must be one of those values. So we can't measure anything. There's certain values we can measure, and there's certain values we will never measure. More often than not, because we're usually dealing with large collections of particles and large collections of measurements, we're usually looking at an average value rather than an individual value. So an average value of a measurement an average value of a measurement is a So we've got certain measurements that are possible. Each measurement might have a different likelihood of happening. And so if we want to get an average, we're going to take a weight of those possibilities. And I have an example for us to think about to make sense of this with rolling dice. The postulate 5 and postulate 6, we're really not going to, well, 5 we're not going to use much this quarter, and 6 we won't use until the end of the quarter. I'm going to put them here. Just moving the desk back and forth for the camera is kind of weird, huh? It's weird to me too, don't worry. Especially when there's only one in this room. Postulate 5 says time evolution. Oh, let me use simpler words. How the system behaves in time is going to depend on the time-dependent Schrodinger equation. Now, in this class, what we're usually going to do is we're going to do separation of variables, and we're going to take the time-dependent part out from the spatial part. And we're going to use one of these tricks. We're going to use separation of variables, and we're really going to spend all of our time this quarter looking at time-independent problems by doing a separation of variables. And then number 6, which most people don't do number 6 on the first or second day of class, but this is one, it's still one of the postulates. It's going to come back in like week 6, so I probably shouldn't say it yet, but it's a wordy one. There's no simple way to write this one. The total wave function Now, of course, you could have read these, but there's little details on top of each of these. So, again, this one is wordy. There's no simpler way to do it. So where this is going to be important to us is when we have systems that have multiple electrons in them. If I've got electron 1 and electron 2, if I flip their positions, if I interchange their coordinates, if I switch it to electron 2 and electron 1, the wave function needs to be essentially inverted from it. It needs to be anti-symmetric. It needs to flip its symmetry. So this is going to be, again, this will come in later. It's going to be this nice thing that makes it, so essentially, you can't have the 2 electrons on top of each other. If I flip the electrons, it needs to like turn the entire thing, not just change the electrons. So the electrons need to like completely change the system. That will come up later. Again, we're not going to use that one for several weeks, and when we use it, we'll have a much better foundation in our mathematics and how we're going to approach our problems. These are the postulates. These get a little bit more complicated. We can think about them with a little bit more detail. I really want to think for a moment about 2, 3, and 4. This idea of, really just 3 and 4. This idea of particular possibilities and the idea of the average of those possibilities. And so I want to think for just a moment about rolling dice. So let's say we're rolling 2 dice. Right? What is this idea of a possibility from the operator? If I'm rolling 2 dice, I've got a restricted amount of possibilities. If I'm rolling 2d6, what are my possibilities? 2. What else? 3, 4, 5, 6, 7, 8, 9, 10, 12. I will never roll 1. I will never roll 2.5. There are only certain possibilities. When I do this action of rolling 2d6, there are certain things that I'm going to observe, and there are certain things I will never observe. Now, is rolling 2 as likely as rolling 7? No, there's going to be a probability to each of these things for how likely I am to roll each one. So if I put this onto a map, there is, let's see here. I'll try to line it up. There is one way to roll 2. That's it. Both of them being 1s. There are 2 ways to roll 3. I can have 1, 2, or I can have 2, 1. There are, is it 4 ways? Why can't I do math in my head right now? Let's see, you can roll, oh no, there's only 3 ways. I made that box too high. there are 3 ways to roll 4. 1, 3, 3, 1, or 2, 2. But I am more likely to roll 4 than I am to roll 2. I can keep going with this. Each one has an extra way. There are 4 ways to roll 5. There are 5 ways to roll 6. There are 6 ways to roll 7. And then it steps back down the other way. Trying to line things up. Right, this is just with rolling 2d6. And I get this function, I get this distribution of possibilities. And if I wanted to, I could approximate this to a curve. Right, I've got this curve of possibilities. And I could relate this to a, let's call this, I could say that's my function of rolling dice. There's some curve that describes my probability of how I'm going to roll things. Now, if I wanted to figure out my average value of rolling, it's my likelihood of rolling 2. And then it's rolling 2 versus likelihood of rolling 2. The probability of rolling 4 and the number of ways. So it's the difference. You have to add up the probabilities. If I want to know the probability of rolling one thing, it would be by comparison to everything else. So the things we can tell from this is we can tell that we have a probability distribution. This idea of a distributed function also works with this idea of just randomized things. We're also going to start using this idea of eigenvalue problems. So this is what this starts to get to. So eigenvalue problems, it's just eigen is the name of a person who came up with this mathematics that described operators that give us particular values. Things where we get only one value out or only certain discrete answers out. So we're going to get this new math to kind of describe how we can get something like this, but with distributed objects. And then we also have a most likely roll, right? We have a most likely result. We can also get our average result by doing the weighted average of everything. With dice, it's a little bit more difficult. Well, it's not more difficult. It's just not as nice. But we can start to look at this and make sense. So this idea of certain values and distributions and some function describing everything, just rolling dice kind of tells us those ideas. So again, the reason I'm going through all of this is because we're about to start really doing quantum mechanics. And a lot of quantum classes just start with doing quantum mechanics. They just start with, let's do the postulates, let's do wave functions, let's do orthonormal basis set. And I want you to kind of see that there's places in your life already where you've seen tools that work for this. They're in classical physics and just in thinking about probabilities. There's places where we've already seen this thing happen. Also, there is going to be a pretty normal pattern to how we solve our problems. So the first thing that we're going to do as we start to work on these different problems, there's kind of just a certain set of things that always happens. The first thing that we're going to do is we're going to define the problem. This is going to be a combination of the coordinates we want to use, the potential energy associated with this system, and any restrictions we might apply. So potential energy is this idea of, the total energy is the kinetic energy plus the potential energy. Kinetic energy is always the same for things. Potential energy depends on which problem we're solving. So we've got to define the problem. What's the coordinates? What coordinates are we using? What's the potential energy? What's the restrictions? Then we go ahead and we're going to determine wave functions. So it turns out that when we start our problems, we usually don't know what the wave function answers are. So we start with a generic placeholder for the wave function. We usually use the Greek letter psi for our placeholder for whatever that answer is going to be, but we don't know at the beginning. We just say, oh, it's some psi. And the second thing we're doing after we define the problem is we determine what those wave functions are. And those wave functions are going to be the thing that completely define the system. So they're going to tell us everything we want. Theoretically, everything we want to know is contained inside that wave function. Then we usually go and we start getting some different things. We determine the energy. If there are multiple psi's, we determine the energy for each of those. This is again going to be some measurable value, some what we call an eigenvalue, but there's going to be some particular measurable that we're going to get, and we have to determine that. We don't know that at the beginning, we have to figure it out. And then the fourth thing that we're going to do is we're going to calculate observables. So after we determine the wave function and after we determine the energy, that's where we can finally get to, okay, so what's the position of the electron? What's the momentum of the electron? How's the electron? And I'm using electron in particular. There's a lot of other objects you can do this for. But for us, in this class, it's usually going to be where are the electrons around a molecule that give rise to those reactivity properties. And it's pretty much going to be those 4 steps for each problem that we do. Okay, that's a lot. Questions so far? Yeah.
Will we be able to see an example of a problem?
Mm-hmm.
Okay.
Maybe not today, but definitely on Thursday we'll see an example of the problem. We'll do a particle in a box and a free particle, which I think is already like 7C. 7B is all about the wave function, so dealing with this first postulate. This is what I'm going to talk about next. Okay, so there's a couple things that we have to do in terms of cementing these postulates into really measurable kind of mathematical ideas. The way that I wrote these down are what I think are kind of like cutesy, easier ways to deal with them. The first postulate kind of has multiple parts to it. So it starts with the system is completely defined by the wave function and also has some particular meanings. So we have the system defined by a wave function. Is the wave function psi. The probability is going to be the absolute value of psi squared. Now this is a little bit of a funny thing to write because most people say, well, isn't the absolute value of psi always, isn't psi squared always the absolute value? We're actually going to have situations where psi could be complex. Instead of, remember, it's just whatever solutions come out from the problem we set up. So some of those solutions could have imaginary parts to them. In that way, we could end up with psi star psi, where this is the complex conjugate This will guarantee, doing psi star psi will guarantee that we end up with real values. We never end up with imaginary complex values when we're trying to deal with our probability. If we're looking at probability over a certain range, we might have a certain area that we're looking at. I just spelled peace wrong. No, P-E-I-C. Right, I use d tau as my generic, like dx, dy, dz, or dr, d theta, d phi, depending on how we're setting it up. So this is going to be our probability. And this also means that if we wanted to get the total probability, we would have to look at the integral right? We'd have to look at the integral of psi star psi, our wave function, over d tau. A handy thing that we will use on occasion is to say that the total probability if we are working with functions that have the total probability equal to 1, that would be a situation where we're dealing with what's called normalized wave functions. You know, probability is nice if probability is a total of 1, that's like 100%. When we originally solved these things, when we determined wave functions, we need to have, they could have all kinds of random values associated with them. We come up with some normalization constant to make it so when we get our total probability, we guaranteed that it's equal to 1. And we'll have some particular examples we can look at that, but we've got to do this integration. We've got to integrate over all space, which means we end up with some other restrictions on our functions. Does anyone remember, okay, 1 through 5 calculus? Ooh, oh right, you all did calculus online. So do you remember, do you remember the restrictions on the function in order to perform an integration? So we need we need that psi. We need that wave. We need that function that we're integrating. We don't have wave function is what we always call it, but you can just call it a function. It's just a function. It's a mathematical function. But we need it to be well behaved. So there's a couple things that we need to have happen in order for this to be well behaved, so we can take the integral. We need psi to be single valued. We need the derivative. We need the derivative to be single valued. We need psi to be finite. We need the derivative of psi. Yeah, I'll just do it for tau, all space. And I'll leave it for just x. We'll do it one-dimensional for now. Right? It applies to all 3 dimensions, but I'll just leave it as x. We also need psi to be continuous. And we need the derivative of psi to be continuous. Now, what do all of these mean? Well, if we wanted an example, single valued was always the one that messed with me the most. I couldn't figure out what that meant when I was in math classes. What it means is you can't have loop-de-loops in it. Right? If you've got something that's got like loops, if I look at this x spot, there's 1, 2, 3 values associated with that x. Not allowed. Right? That's not single value. You can't have that happening. For it to be finite, we can't have things that Blow up to what? I didn't mean to draw it into the other one. Just got carried away. I guess that's what finite is, right? If things blow up to infinity, it's not finite. Right? So that's going to be another problem we have. That's something else that can't happen. And then we need it to be continuous. So something that's continuous means we can't have situations where we've got like jumps. That also isn't a possibility. Right? Those are the situations that we can't have. We can't have it have like weird jumps or breaks in it. It doesn't have to be a jump. It could just be like a break. If I just have a break right there, that's also not good. Functions like that would not make good functions for our class. Functions where we've got loop-de-loos, where things are overlapping on each other, those are also going to be functions that are not good for our class. Those are going to be things that don't work well. And then we're also going to have, well, let me give you an example of a function that is good. If I have some oscillation that's just, dampening down, going towards 0, that's a function that looks pretty good. This is single valued. If I look along my x, there's only one value on the y-axis for each of my x values. It's crashing down towards a finite value. It's not exploding off towards infinity. It's also a good thing. And it's continuous. There are no breaks in the lines or anything like that. So that's a good function. This would look like a sine wave with an exponential decay or something like that, right? Multiple functions put together can make a well-behaved function. Question?
You mentioned something about imaginary numbers. Can you take the derivative of imaginary numbers?
Yeah.
Oh, honestly, I didn't know that.
Yeah, you can take the derivative of imaginary numbers.
Okay.
So like if you have an I to the x, because I is just a constant, it comes out of the derivative and you just take the derivative of the x part. It's a problem when we want to start making measurements, because if you've got an imaginary number, like how do you observe that in real space?
Yeah, how would you plot it, I guess?
We would not plot, so we would plot it kind of two different ways. We would usually plot not the wave functions by itself, but we're probably going to plot the probability of the wave function to guarantee that we're plotting a real function. Otherwise, we'd have to plot in complex space. We could plot in complex space and look at that, but it's not as useful as just plotting the probability, because then we've got those guaranteed real values. We're also going to have, sometimes we're going to have wave functions that are just completely real. So we've got a little bit of time left. I want to talk about two more things. I want to talk about like 10 more things, but I'm going to try to restrict it down to just like 2. So we've got some restrictions on our wave function. We've got these things that have to be true when we start looking at wave functions. We still have no idea what the wave functions are because we haven't defined a system yet. We haven't defined a problem to solve yet. So this is all just kind of like weird conceptual thinking at this point. These kind of restrictions that come out to make sure we can do the math, do the work that we need to. The other thing, well, let's do this. So the second postulate kind of talks about these operators. Do I want to do this? Let's do this. Okay. So we're going to end up with situations. We've got a bunch of different operators that are going to come out. I could spend the next like 10 minutes writing out the common operators we're going to see. But there's actually something else I want to do. And that is, I want to start thinking about, well, where do these wave functions come from? And what kind of wave functions are we going to be dealing with? So we're going to be solving differential equations. 1 through 5, solving differential equations. It's not as bad as you think. Let's look at an example. So I have this system of equations. There's a bunch of equation examples that I have that are going to follow this. This is going to be kind of the problems that we set up. I've got the derivative of a function, gets me a constant k times that function. Now what I want you to do is just with the people around you, what are some functions where you take the derivative and you get the same function back? Discuss.
It's not a function. Yeah, that is a function.
I heard e to the x. What's another one? Oh, 0. Well, yeah, 0. Okay, let's do that. Let's talk about that. We're going to talk about that one because it's a boring answer. But 0 is, because we get 0 as an answer sometimes, and we ignore it because it just means nothing exists. Another one that's possible is, and I'm going to generalize this, any e to the ax would work. Right, so we could have any constant up there. We could even have e to the ax, right? We could have it be imaginary. In each of these situations, now 0 is a silly one. Was that the one people were debating where it's like, that's not a function, that's, you know, like. So what happens is, if we get zeros, because we get zeros as answers every once in a while, having a function equal to 0 essentially says we're not solving a problem. Nothing exists. We would call this we call it a null set, or like I just call it a boring answer, right? It's just like no function. If you got no function, the derivative of nothing is nothing. That's boring. Right? These are more interesting. Let's look at the e to the ax. So if I'm going to switch that from ax just for fun. What am I going to switch it to from a? Okay. Right? If I have d by dx of e to the kx, I take the derivative, I get k e to the kx. That gives us one possible solution. F of x is equal to e to the kx. That's one of our possibilities. So what we just did is we just did number 1 and number 2 for our typical problems. I gave you a system, I gave you a problem, and we said based on our knowledge of math that we already have, we can come up with an answer to that problem. Let's do another one. Make sure I set this up correctly. I'm picking particular things on purpose. Let's say we look at this. Right, I'm trying to make math less scary. What are some functions that would work for this? Discuss with your neighbors.
Cosine of k of x or something like that.
Either side is
What else?
sine.
Sine of k of x. What else?
Combination of cosine and sine.
Yeah. Combination of cosine and sine would work. There's another function that also works. Yeah.
E negative kx? Yeah.
Well, not e negative kx. Is it e negative kx? I think it's e I kx.
Oh.
Right, because then you take the derivative once. Because if it was negative kx, you'd get a negative from the first derivative. Second derivative would make it back positive. If it's I, you'd have I times I. That would get you the negative sign. So we end up with these 3 different answers that are possibilities. Now, we just did number 1 and number 2. We defined some problem, and we determined functions that work for that problem. And this is what we're going to be doing all quarter. And it turns out that this is usually how we're going to go about it. There is a different way to solve differential equations that involves doing power series expansions and different mathematics for solving what functions work here. We're going to mostly depend on things we already know or work that other people already did. Right? When we start solving really big problems like harmonic oscillators, we're just going to grab the Hermite polynomials and say that's the answer to those differential equations. And you know it was really hard to solve because the person who solved it got the answers named after themselves. So there's another set of problems that we're going to solve, and we're going to use the Laguerre polynomials. A problem so hard that the person who solved it got the answers named after themselves. And then we'll get the same thing with the genre polynomials, right? Again, they're going to be mathematical things we could do, but we're just going to use the answers that other people have already generated. Because they, you know, famous, mostly French mathematicians from the 1700s and 1800s, who were just like, I feel like solving problems. How would I solve this? And they mostly did it through Parry series expansions, Taylor series. We're just going to use their answers, though. So we've got different ways that we can write down different answers to this, and we can start seeing how we can do the first bits. If we define a problem, we can start coming up with some functions that work for that problem. We can then start to find other things that work for that, right? So if I call this, I can change this around a little bit. I could just say, right, if cosine works, do I want to do that right now? Right, so I could essentially have, instead of k, I could have some like a there, and then I'm going to end up with a equals. So a could be like any number, and I'm going to relate it to this k value. Typically what we're going to find, no, I don't want to do that yet. I'm thinking of a problem too far ahead. But essentially what we can do is we can say, look, I can do this for some generic, I don't need to be restricted by this k yet. But eventually I'm going to solve, and the constants inside here have to be equal to the constants outside here. So let's go ahead and solve this, and I'll show you what I mean. Let me do this for, I'm going to pick a random, I'm going to pick just a little random thing. I'm going to do an example. Let's say we do cosine of a over 2x. Then I'm going to take the derivative twice. I'm going to take the first derivative. Cosine goes to sine. So I'm going to get a over 2 sine a over 2x. If I do d by dx of my function, and this is usually how I do second derivatives. I don't do them both at the same time in my head. And then if I do the second derivative, so I'm going to take the derivative of this. Sine is going to go to negative cosine. So I'm going to get negative a squared over 4 cosine a over 2x. E to the ikx is still over here as a possibility. Now, what I do in order to figure this out is I set these equal to each other. So I say a squared over 4 cosine a over 2x is equal to negative k squared a over 2x. Right? This gives me some relationship where any value I had now has to be related to my k value. So as I set these different problems up, I don't need to know what this k value is beforehand. I can make up a function and then figure out what restrictions I have on the function to solve this. So there's some relationship of whatever this k value is to the generic function that I want to make up. What we will do next time is we'll start looking at how we apply a little bit of this thinking to things like particles moving in free space. We'll talk about some about our operators that we're going to be using. So we've essentially, let me just double check something to make sure I'm not lying to you. And so here's the thing about 7. Oh no, it's fine. We've essentially already done most of 7b. And we've started talking a little bit about some of the stuff in 7c already. Just to give you an idea of where we are with things.